This is the second part of the Chapter 3 lecture. We began this part of the lecture with the definition of mass compared to the definition of weight. Now the definition of mass comes from Chapter 1 that we had in the first semester, and it's simply the amount of matter in an object. So if a substance has more matter, then it's obviously going to have more mass. Now matter can come in three forms, either solid, liquid, or gas. Now the weight of an object actually depends on the force of gravity acting on the object. So your weight can change if you move from one location to another, such as moving from the Earth to the Moon, but the mass will not. Now the unit for weight in the English system happens to be pounds. In the metric system it's called a newton, and the mass unit in the metric system we know is a kilogram. So if you'll look at the example that I have over on the side, you can see that the mass of the person on the Earth is 80 kilograms and their weight on the Earth is 176 pounds, but when you move that person to the Moon, their mass stays the same at 80 kilograms because again the mass doesn't change when you move from one location to another, but you'll weigh less because there's less gravity on the Moon, so your weight will drop to 29 pounds. So that's basically the difference between mass and weight. What you need to remember is mass doesn't change when you change your location, but weight is depending on gravity, so it does change when you move from one location to another. Now the density of an object is the next topic, and we did a computer activity in our class as an introduction to this topic, so I'm not going to spend as much time explaining what density is because the students of mine have already done a density activity. But the density is simply a ratio of the object's mass and its volume, and density doesn't depend on the size of the sample you have. So for example, if you have a little piece of gold or you have a large piece of gold, it should have the same density because it's simply a ratio of the mass and volume. So as you make a smaller piece of gold, the mass decreases but also the volume decreases. So the density would stay the same. The ratio would be identical. Now the density of an object will determine if it will float or sink in another phase. So if the object floats, it's going to be less dense than what you throw it into, and if it sinks, it's going to be more dense than what you put it into. Now usually we put objects into water, or we have gases and we want to see if they float or sink in air. So you need to know these constants. The density of water is 1 gram per milliliter, and the density of air is 1.29 grams per liter. And the reason we have the difference in the volume unit is that with solids and liquids they're usually measured in milliliter volume units, but in gases we have it 1,000 times bigger, which is a liter volume unit. So those are the densities that we compare substances to if we want to see if they float or sink in air or if they float or sink in water. And the formula for density is just mass divided by volume, and I show the students this little density triangle. If you imagine covering up the letter that you're trying to solve for, you can see mathematically what you're going to need to do. So if you cover up the letter M, you'll see that the formula reads density times volume. If you cover up the letter D, we see that mass is on top and volume is on bottom. And if you cover up the letter V and trying to solve for the volume of an object, you would take its mass, which is on top, divided by the density, which is on the bottom. So this is a little algebraic trick that I learned in grad school. Now we're doing some practice problems on the next slide. It says the density of gold is 19.3 grams per cubic centimeter. So how much would the mass of a bar of gold be if it has a certain length, width, and height shown on the screen? So we're trying to figure out the mass of the object, so we need to have the density and the volume. We already know the density, that was given 19.3, but in order to find the volume of this bar of gold, we have to take the length times the width times the height. And they're all in centimeters, so we can multiply them together to get an answer of cubic centimeters for the volume. Then we're going to take that answer and multiply it by the density that was given, and we have 19.3 multiplied by our volume answer, and you end up getting around 25,794.45 grams. And I'd like to round this off to the correct number of significant figures because that's one of the things that we do in this chapter. We round off our final answers. And because our length, width, and height only had two significant figures, we can only have two significant figures in our final answer. So we can round it off to around 26,000 grams. And if you want to know that in kilograms, it's 26 kilograms because you can move the decimal point 3 times to the left. And if you want to convert it to pounds, you can multiply by 2.2. And you can see that a bar of gold would weigh around 57 pounds. In the second example, it relates to something we did on the computer activity. And it's showing a picture that has a block of wood in fresh water. Now you can see that the block of wood is obviously floating in the fresh water because the block of wood is less dense than the water. And now we want to know what will happen if you put this same block of wood in salt water. In picture A, we see that the block is sinking, In picture B, it's hovering, so that would mean it has the same density as the salt water. In picture C, it's identical to our original picture. And in picture D, it's floating higher. So what would happen if you put it into salt water? And the answer is it would float higher up, because salt water is more dense than fresh water. So objects would float higher in a more dense liquid. In example number 3, we just want to ask if this object will float or sink in water, and it's specifically asking if it will float in water, and you can calculate the density if you wanted to, but if you just look at the mass, it's bigger than the volume, so we know that the density is going to be greater than 1, so this object will sink. So in the answer to the question, will it float? The answer is no, it will sink because the density is greater than 1. Now again, you could calculate it by taking 27 divided by 25, but qualitatively speaking, you can see that it's going to be greater than 1, so you don't really have to do the math. On the next slide, we discuss the temperature scales that we use in science classes. Temperature is the hotness or coldness of an object, and basically I discuss a little bit about the difference between temperature and heat. Heat is a form of energy that moves from hot objects to cold objects, and temperature basically tells you which object is hot and which object is cold. Now, the Celsius temperature scale was developed by some dead white guy. We don't discuss the names of the people that invented the temperature scales too much. You don't have to know them on a test or anything. But anyway, the Celsius temperature scale is based on the freezing point and boiling point of water, a wonderful standard to use. So the freezing point was designated as 0 degrees Celsius, and the boiling point is designated at 100 degrees Celsius, and you make your thermometer that way. The Fahrenheit temperature scale, we discussed a little bit in class how wacky it is. If you're really concerned about what Fahrenheit is based on, you can look it up on the web, on Google websites or something like that. Wikipedia is a good site to look at what Fahrenheit's based on, but we don't use it in science classes, so I'm not going to worry about it in this lecture. The Kelvin temperature scale, though, was invented because if you're going to use temperatures in math formulas to do calculations in science classes, you can't be using 0 in your math formula if you're going to multiply temperature by some other constant or by some other number, because it would just make the whole formula 0, and you can't divide by negative numbers or you screw up some of your math calculations. So they had to come up with a scale that doesn't involve 0 as a realistic temperature or negative numbers as temperatures. So the Kelvin scale is actually based on the lowest possible temperature that you can ever have, and it's called absolute 0, and that's technically the place where all molecular motion would stop. Now it's a theoretical temperature. You really can't actually get a substance to absolute 0. It's one of your laws of thermodynamics, and if you take AP chemistry, we talk a little bit more about it. But basically, you can't ever get to absolute 0, but the only difference between the Kelvin temperature scale and the Celsius temperature scale is this absolute coldest temperature, which happens to be negative 273 degrees below 0. And that's in Celsius. So if you want to change from Celsius to Kelvin or Kelvin to Celsius, you just have to add or subtract this factor of 273 degrees. If you're going from Kelvin to Celsius, you have to subtract 273, and if you're going from Celsius to Kelvin, you have to add 273. And the way I have my students remember this, even though I do give them the formulas for this conversion on tests and quizzes and stuff, but the way I remember it is that if you're going from the letter C in the alphabet to the letter K in the alphabet, you have to add letters. So if you're going from Celsius to Kelvin, you have to add 273. And if you go from the letter K back to the letter C, you have to subtract letters, so you subtract 273. The practice problems are very simple. We have Celsius to Kelvin, so you add 273 and you get 298. Going from Kelvin to Celsius, you subtract 273 and you get an answer of 200 degrees Celsius. So that's all I have my students do for measuring temperature, just basically knowing what the Kelvin scale is based on, knowing what the temperature in Celsius is based on, and then converting from one to the other. And then I have a picture that just shows the different temperature scales next to each other, and then some common temperatures like boiling water, your body temperature, room temperature, and etc. And you can see in absolute 0 we have 0 degrees Kelvin, negative 273 Celsius, and in Fahrenheit it happens to be around negative 460 degrees below 0. The last slide discusses percent error. A percent error is a way of representing how accurate a measurement is, or how accurate a value is, and accuracy tells you how close to the right answer you are. So if you remember the bullseyes from part 1 of the lecture, your accuracy is how close to the bullseye you are, and this is expressed as a percent. And so how far off of the right answer are you in terms of a percent? You can do this calculation. You take the absolute value of the accepted measurement minus the experimental measurement. That's what you would get in a lab if you ran an experiment excuse me, and if you divide that by what the correct answer was supposed to be. So you subtract your answer from the right answer, and then you divide by what the right answer was supposed to be. We look at an example problem, and we have a student measuring the density of a block of aluminum, and they came up with an answer of 2.96 grams per milliliter, and then the correct answer for the density of aluminum is 2.70 grams per milliliter. So we can figure out their accuracy by subtracting their measurements, and we can again take the absolute value of that, and then we divide by what the right answer was supposed to be, which was 2.70, and then you could express that as a decimal, but we like to express it as a percent, and if you round it off to 3 sig figs, you get 9.63%. So their error was only 9.63%. So that's percent error. And again, I give the students the equation, and they just have to know what numbers would go into each spot. So that's basically the Part 2 lecture, and we break up the chapter in 2 parts because there's a quiz over significant figures and scientific notation, and then we have another quiz over density of the metric system, and then we put it all together with some of the other topics like temperature and percent error. So that's basically the lecture for Chapter 3.